The purpose of this video is to look at the second derivative and determine what the second derivative tells us about an original function, and in particular the concavity. So let's begin by defining concavity. Concavity refers to the curvature of a function. And what we mean by curvature is either a function or part of a function can be concave up, or the function can be concave down. Those are the two types of concavity that we're looking at. And where a function changes concavity, in other words, the function changes from concave up to concave down, or from concave down to concave up, is called a point of inflection. So it is a point where the function changes concavity. So if you take a look at the three functions that I have below, notice that the first function is the original function f of x. The blue function is the first derivative of the original function, and the red function is the second derivative of the original function. So it appears that in the original function it looks like we have a cubic function. And the first thing that it asks you to do in this exercise is examine the graph of f of x and determine the intervals of concavity and any points of inflection. Well, it's easy to see that this piece of the function is concave down simply because the graph opens down in that region, and in this region the graph is concave up because the graph opens up. And kind of right in the middle there, this is an easy one to identify the point of inflection without doing a lot of analysis. The point of inflection where the concavity changes is right here, point of inflection. And it occurs at x equal to 0. That is where the curve begins to make its change from concave down, opening down, to concave up. Alright, now we want to jump over to the second derivative graph, the red graph on the screen. And the second question says, alright, we've identified the intervals of concavity. We've said that the function is concave down basically from negative infinity to 0, and the function is concave up from 0 to infinity. So let's take a look at the red graph, the second derivative graph, and describe the behavior of the second derivative on these intervals. So if you look at the red graph from negative infinity to infinity, which would be this, to 0, to this region of the graph, you'll notice that the second derivative in that region is negative. And if you look at the concave up interval of the original function, which would be from 0 to infinity, you notice that the second derivative is positive in that region. And then finally, if you look at the place where the point of inflection occurred on the original graph, you'll notice that the second derivative at this particular value of x, which is 0, turns out to be 0. So this is one example, but it is true that wherever an original function is concave down, the second derivative is negative, and wherever an original function is concave up, the second derivative is positive. So those are mysteries that the second derivative can reveal to us about an original function. We did number 2 and number 3. Again, number 2 said compare the second derivative. So if the second derivative is positive, f of x is concave up. If the second derivative is negative, the original function f of x is concave down. And describe the second derivative at the points of inflection. Well, wherever the second derivative is equal to 0, there is a possible point of inflection. And it's very similar to the first derivative test, just like when we're trying to find local max and local minimums. We have to find the critical numbers, and the critical numbers don't guarantee local max and mins. they simply are possible local max and mins. That's the same case with the second derivative. The second derivative can identify possible points of inflection, but it's our job to determine whether they actually are points of inflection. Alright, now let's move on. Not only can we get information about concavity from the second derivative, but the first derivative can also give us information about concavity. Now remember, we had already identified that the concave down interval was from negative infinity to 0, and the concave up interval was from 0 to infinity. Alright, now let's take a look at the first derivative at those intervals. So if I look at the first derivative from negative infinity to 0, which is my concave down interval on f of x, notice that the first derivative is decreasing over that entire interval, which makes sense because notice his derivative, which is the second derivative in that region, is negative. So wherever the first derivative decreases, his derivative would be negative. So the first derivative can also help us to find out information about concavity if we know what's happening with the behavior of the first derivative. So look at the graph of the first derivative, number 4. Describe the behavior of the first derivative. So what we see is when the first derivative is decreasing, now not negative, but decreasing, the original function is concave down, and when the first derivative is increasing, not positive, the original function is concave up. So if you look back up at the first derivative graph, here's the region where my original function was concave up, and the first derivative graph is increasing. Now finally, if you take a look at where the point of inflection was occurring, we said we had a point of inflection occurring at x equal to 0. Well, if you look over here at x equal to 0, wherever there is a point of inflection on the original function, point of inflection of f of x will appear as a local max or a local min on the first derivative, which makes sense because we said over here on the second derivative, wherever the second derivative is 0, we have a possible point of inflection. Well, that makes sense that his derivative, the derivative at this local minimum, would be 0. So describe the behavior, number 5, of the first derivative at the points of inflection identified in the original number, I guess. So we said the first derivative has a local max or min at a point of inflection on f of x. And it's important that you understand how to identify concavity using the first derivative as well as the second derivative. However, in these examples, in this particular example, we're going to look at concavity using the second derivative. Now, take a look at the first function. I'm not going to actually do this example because the second example is a little bit more challenging. But this function is a fourth degree function. It's pretty easy to find the first and second derivative of. So I want to take a look at a problem that involves a little bit more work. So let's look at the next example. In this problem, the second derivative function has already been given to us, so we don't even know what the original function is. And using this second derivative, we are to identify the intervals of concavity and locate any points of inflection. Alright, since we already have the second derivative, the first thing we need to do is to identify possible points of inflection, just like possible points of inflection. Now this is very similar to using the first derivative test to get local maximums and local minimums. Remember, when we do the first derivative test, the first thing we do is take the first derivative, set it equal to 0 to identify possible points of inflection. So, likewise, I'm going to take my second derivative, set it equal to 0, and just like the first derivative test, wherever the second derivative is 0 or undefined, we have possible points of inflection. So I'm going to begin by setting the numerator equal to 0. 3x squared plus 4 is equal to 0. So 3x squared is equal to negative 4. X squared is equal to negative 4/3. And if I try to take the square root of a negative number, I'm not going to get anything, so I don't get any possible points of inflection out of the numerator. Alright, setting the denominator equal to 0, x squared minus 4 equal to 0, I get x equal to plus or minus 2. So these two values of x are where my possible points of inflection may occur. The second thing I'm going to do is notice that I said points of inflection. They're possible points of inflection. Now I have to decide whether these values, whether points of inflection actually occur, or whether they're not points of inflection. So to do that, I'm going to set up a second derivative number line. Now make sure that you name your number line second derivative, because the second derivative tells us certain things about the original function, and the first derivative tells us certain things about the original function. So we're not finding maxes and mins on the original function, we're looking for points of inflection. Alright, just like the first derivative test, I'm going to put my two possible points of inflection on my number line. Then I'm going to choose values in each region to test out. And again, I'm looking for whether the second derivative is positive or negative, because if the second derivative is positive, I know the original function is concave up. If the second derivative is negative, the original function is concave down. When I choose a number like negative 3, I'm going to substitute it into the second derivative, remembering that I only need to know the sign. Well, if I substitute negative 3 into the numerator is going to always be positive because I'm squaring a number, multiplying by 3, adding 4, and dividing by 10. So I know that I have a numerator that's always positive. If I substitute negative 3 into the denominator, I'll get positive 9, take away 4, which is 5 cubed, which is a positive, and a positive divided by a positive is a positive. Now notice on my second derivative number line, I'm all about concavity, so I put a smiley face. In other words, that tells me that the original function is concave up. When I choose a number between negative 2 and 2, like 0, we already said that the numerator would always be positive. The denominator in this case would be negative, and a positive divided by a negative is a negative, which tells me that the original function is concave down, so I'm going to put a frowny face there. Choosing a number greater than 2, like 3, the numerator is positive divided by the denominator. When I substitute a 3, I'll get a positive number, and a positive divided by a positive is positive, so the original function is concave up. Alright, so when I interpret my number line, remember it's all about the original function. We're always looking for information about the original function. So what that tells me is that a point of inflection, well, I already kind of used my abbreviation, a point of inflection occurs at x equal to negative 2 and x equal to 2, and are f of negative 2 and f of 2. Actually, we're not looking for local max and mins. Let's regroup that. Let me erase and start over. I apologize, because it says we're looking for points of inflection. Alright, let's try again. A point of inflection occurs at negative 2, f of negative 2, and 2, f of 2, because the second derivative changes sign at these values of x. Okay, so that's how you use the second derivative to identify concavity. Now, in a future lesson, what we'll be doing is we'll be using the first derivative as well as the second derivative to find out as much information as we possibly can about the original function, and then without even knowing the original function, we'll be able to describe its behavior, its local maximums, its local minimums, the concavity. So anyway, I hope you find this lesson to be helpful.